Welcome everybody to this webinar. We will wait for a couple of minutes just to let everybody in, and then we start. Okay, so welcome to this TREX webinar, which is the third of a series of webinars that the TREX Center of Excellence has been running over the last 2 years. My name is Sara Pittonet. I'm the outreach manager of the TREX Center of Excellence, and I have the pleasure to welcome you today. So let me just give you a short introduction of today's webinar. So between 2020 and these days, actually, the TREX Center of Excellence brought together European scientists, high-performance computing experts and SMEs to develop a series of flagship quantum Monte Carlo codes to exploit the capabilities of the recent exascale computers at its highest. That's the purpose of the webinar today. We are reaching the end of our journey for the TREX Center of Excellence, and we're happy to give you an update of the TREX codes today with the experts from the project that contributed to their development. So I'm very pleased to give the floor to our speakers for today, and we start with a welcome overview from Michele Casula, head of the Quantum Theory of Materials group at IMPMC CNRS. So Michele, over to you.
Okay, thank you, Sarah. Yeah, so I'll be speaking on behalf of Claudia Filippi, who's the coordinator of this Center of Excellence. Unfortunately, Claudia was not able to join today the webinar, so I try to do my best to replace her. And I'll give you a brief overview of the Center of Excellence. So as for the historical perspective, TREX has been funded by the Euro HPC committee, and it started as project on October the 1st, 2020, and it will end, as Sarah mentioned, in a couple of weeks at the end of March, after a journey of more than 3 years, actually 3.5 years. So the goal of this Center of Excellence has been to sort of develop quantum Monte Carlo methods. So quantum Monte Carlo methods are the main focus of this center. And the reason is that quantum Monte Carlo methods are, in most cases, the most accurate methods available to solve the quantum many-body problem, in particular to get accurate properties of molecules and solids. So they provide benchmark results in many situations, and in other cases, they provide new insights in terms of predictions of physical properties and also chemical reactions. The drawback of the quantum Monte Carlo methods is their cost. So they are very accurate, but they are also very costly, although many of them are not exponentially costly, so they are still bearable by regular CPU architectures. And moreover, they can be massively parallelizable. So they can really be the best methods to be used in high-performance computing architectures, where one needs to exploit the multiple hybrid architectures with many cores and possibly also many accelerators. Given this background, the goal of the Center of Excellence has been to develop the existing QMC codes to make them also more accessible to a broader community, and support them to the pre-Exascale and Exascale systems. The idea was not only to develop the existing codes, but also to provide new libraries. And these libraries are meant to make a researcher's life easier if this researcher wants to use QMC methods for his own research, for his own activity. And one of them, which is I would say the most relevant one in terms of perspectives, in terms of the future of the legacy of the center, is QMCkl. So QMCkl is a library that is supposed to contain all the main routines, the main ingredients needed to run a quantum Monte Carlo calculation and the quantum Monte Carlo workflow. And these can be linked to existing codes, not necessarily quantum Monte Carlo codes, and by using the routines included, one can really run, construct his own, her own QMC workflow. And then the second library provided by TREX is the TREX IO library, and this one is meant to favor the exchange of input and output files between the QMC codes within the TREX Center of Excellence, but not only. So we'll see, I'll see you in the next slides what are the features of these two libraries. But before getting there, I'd like to list here and to mention all partners of the Center of Excellence. So this center gathers scientists in quantum chemistry, physics, and machine learning as well, together with experts in software development and high-performance computing, like, for instance, the CNECA Center. But not only, also, it includes also communication SMEs, like Trust IT, which organized this webinar, and also tech SMEs like Megaware, that is developing HPC solutions for high-performance clusters. And of course, not only the institutional partners, but I'd like to mention also all the communities, the user communities that joined us during this journey, during this 3 years period, by attending our webinars, our events, and the many schools we organized to diffuse the theoretical background behind quantum Monte Carlo methods, and also to organize hands-on sessions to make the use of our codes more easy and also broader. All right, so that's a picture, HammerCore picture from 2022, where we organized the hackathon, the second hackathon of TREX in Versailles. After that, let's go through the list of codes that belong to the TREX. So that's the list here. You have CHAMP, QMCkl, TurboRVB, NESI, Quantum Package, and GAM Core. So you'll see an overview of each of them later during this webinar. And of course, I need to mention also that the machine learning tools that has been developed to integrate the quantum Monte Carlo results into a generation of machine learning potentials, or to use neural network with functions within a quantum Monte Carlo framework. Some effort has been devoted to couple the AIDA workflow manager with some of our QMC codes. Last but not least, the libraries, QMCkl and TREX.io. And for QMCkl, I give here an example. So you have here an example of the calculation adjuster factor using a QMCkl routine, and that this has been embedded into the CHAMP code. And you can see here that by optimizing the procedures within the QMCkl, you can improve upon existing high performance libraries like MKL. And that's an example here on the right-hand side. You have the speed up as a function of the system size. And you can see that if you use the routines implemented in QMCkl, you get even a better performance, which is even better than the MKL one that exploits, for instance, matrix multiplications in the BLAS routines. And this has been achieved thanks also to a tight collaboration with software experts and software engineers at the University of Versailles Saint-Quentin, who developed specific tools to profiling the codes like Macau. And the optimization effort has been one of I would say the main directions taken during this time. And then after that, let me just give an overview on the TREX.io library. So we have seen the performances reached by QMCkl. Now TREX.io. TREX.io, the difficulty there is not about performance, but it's about, if you like, the managing the workflow, the complex workflow behind any QMC calculation. So behind any QMC calculation, you should combine the with function generation with sampling of the configuration space, computing observables on top of the configuration generated by quantum Monte Carlo, and finally get into the physical properties. So there is a long way to go, and each step should be sort of controlled. And sometimes the interface between all these steps is hard to put in practice. That's why we developed a library which is able to interconnect different QMC codes to enhance the interoperability between them. This goes beyond actually the ensemble of the group of our QMC codes. It goes beyond because it's able, this TREX.io library is able to benefit from the input and output of other codes like Python SCF, like games, like Gaussian, So we can really have a hierarchy of different quantum chemistry calculations and import and export the information from one code to another to finally achieve the last step, which is hopefully the most accurate, provided by the quantum Monte Carlo calculations. All right, so my time is over, and I leave you with these two web addresses. One is for that is the TREX website, and the other one is the TREX repository where you'll find all relevant information, both for both all the events and made during this time, and also for the future perspectives, and also the information about the codes developed, the libraries we provided, and also the publications we made during these 3 years journey, as Sarah defined it. Thanks for your attention, and I give back the floor to Sarah.
Thanks a lot, Michele, for this overview. And now we can dive into the individual codes. So I'm happy to welcome Ali Alavi, Director of the Max Planck Institute for Solid State Research, who will present the NICI code.
Yeah, sorry, I'm unmuted now. So I will just briefly present the NICI code and what it can do in just a few short slides. So NICI is a stochastic full CI solver. So it's in some sense, it uses quantum Monte Carlo concepts to solve, to form a stochastic diagonalization. So it's slightly different to the conventional forms of QMC, which propagate, let's say, real space walkers. So instead of NICI, we work with the second quantized Hamiltonians. So these are basically quantum chemical Hamiltonians. And the idea is to try to get a full CI or near full CI solution for that second quantized Hamiltonian. It's got a number of, let's say, special characteristics. One of them is that it deals also with transcorrelated Hamiltonians, which I'll mention briefly in a second. So it does more than just the standard Schrödinger type of problem as well. Now, these transcorrelated Hamiltonians, they require the method to be able to handle non-Hermitian Hamiltonians and also Hamiltonians with the three-body interactions. So the form of these transcorrelated Hamiltonians are basically similarity transformations in which the similarity transformation is done with respect to Jastrow factors which have been obtained through a variational Monte Carlo procedure. So these Jastrow factors involve functions, pair correlation functions, which are generally speaking quite complicated, and which lead to three-body interactions within the transformed Hamiltonian, and which have to be then dealt with. And the stochastic methodology of NICI is quite well suited for dealing with these what are in fact 6-index tensors, which have to be sampled. So let me just say that the actual methodology, the QMC methodology, is based on annihilating random walkers, so walkers which have a positive and negative sign which can inhabit either slated determinant spaces, that's the simplest form of second quantization, or spin-adapted Hilbert spaces, in which you can also fix the total spin quantum number. So we have a particular emphasis within this methodology to be able to handle open shell problems, systems with many open shell orbitals, for example, iron-sulfur complexes. In terms of transcorrelation, one of the benefits of using this methodology is that you can achieve essentially basis set complete results already with moderate size basis sets, for example, triple zeta, where you would otherwise, for a standard non-transcorrelated method, require quintuple zeta size basis sets to be able to get to the same level of accuracy. NICI itself is a highly parallel code, and that's thanks to this sort of QMC concept which underlines it. And we can both go to huge populations of Walkers. This is an example of a chromium dimer calculation where we go up to about 1.6 billion Walkers. And the plot here shows the strong scaling, the observed strong scaling, where you have a linear decrease in computational effort as you increase the number of processors up to the roughly 20,000 or so, which is the largest that we've been able to use. And then finally, I should say that we're extending this methodology now to move beyond stochastic full CI, but also towards coupled cluster methodologies. That is to say, to do transcorrelation within coupled cluster methodologies. And that enables us to improve the accuracy of the coupled cluster by sort of importing these quite sophisticated Jastrow factors, which we obtain from standard VMC. And in this plot, we show that with transcorrelated essentially CCSD, or a variant of CCSD that is a little bit cheaper than CCSD actually, we can achieve accuracy that is comparable. To the what is often considered to be the gold standard, which is explicitly correlated CCSD brackets T. Okay, that is essentially all I wanted to present today.
Thanks a lot, Ali. If there are any questions in the room, feel free to write them down in the chat or raise your hand. We might welcome them now, or we also have some time at the very end. But feel free, to give us a sign. While we wait for any brave, I welcome Kasia Bernal, professor at the Institute of Physics and leader of the quantum chemistry group at Lodz University, to give us an overview of GAM-Core.
Thank you, Sarah. So good afternoon. My name is Kasia Bernal, and I'm one of the developers of the GAM-Core code. The other developers are Michał Chapka, Marcin Modrzejewski, and Michał Przybytek. They are affiliated with the University of Warsaw. I'm from Lodz University of Technology. So first, I'm going to tell you a few words about what you can do with GAM-Core. It will be more about what you can do than about the code itself. And I will show the capabilities of the code on two examples. So first, let me say that GAM-Core is not a quantum Monte Carlo code. It's a deterministic code for doing quantum chemistry calculations. And the main functionalities of the code are calculations of the correlation energy using various methods and of molecular interaction energies. So it's not a standalone code. It has to be interfaced with an external code for 1 and 2 electron reduced density matrices. So you have first, to use GAMCore, first you have to run wave function calculation with another code and produce reduced density matrices to be able to use functionalities of GAMCore. So at the moment, GAMCore is interfaced with a few popular quantum chemistry codes like MolPro, Dalton, Quantum Package, and Orca. But it can also work with any other code which uses TREXio library because it has TREXio incorporated inside. So as I have mentioned, there are two main functionalities. So first I will talk about electron correlation energy calculations with GAMCore. So the example here is that imagine that you have run wave function calculation or DMRG calculation. So you have run wave function calculation within a space of given space of active orbitals, and there is a lot of correlation missing, the out of active orbital correlation. So for that, to add this missing correlation, the dynamic correlation, you can use GAMCore, and for that purpose, you have to run first the calculation with the external code, and as I said, produce and dump 1 and 2 reduced density matrices. So the unique feature of the methods that are implemented in GAMCore is that we only need 1 and 2 density matrices, electron density matrices, not higher order than that. And then there is a special method implemented in GAMCore, which is based on adiabatic connection method. So you can run GAMCore for that calculation of adiabatic connection. And as a result, you get the correlation energy, which is added on top of your DMRG or CAS or CIPC energy. So at the moment, the limit for the basis set size of GAMCore for this kind of calculation is over 1,200, over 1,000 basis set functions. But the good thing is that you can correlate as many as 60 active orbitals. So this is our record. It's more than you can do if you use, for example, perturbation theory methods. The recent developments for this part of the functionality of the code is that we have added Koleski decomposed 2 electron integrals on the fly. So now there is no need to dump 2 electron integrals from the external code, which of course saves you a lot of disk space because the 2 RDMs in the active space do not take that much space. And here is an example of the state-of-the-art calculations with GAMCore for the correlation energy. We have been investigating recently polyacenes, which are molecules which can be seen as molecules consisting of fused benzene rings. So we were able to run calculations for 15 fused benzene rings, which makes 58 electrons in 58 pi orbitals. So this is our record. So we could run calculations for the dynamic correlation energy with the adiabatic connection method for 58 active orbitals. And this has been done in collaborations of this project with experimentalists for the purpose of elucidating the open shell the biradical character of the long polyacenes. Thanks to these calculations, we could show that long polyacenes indeed show open shell character. Okay, the other functionality of GAMCore is molecular interactions, but there's a special method that is implemented in the code, and this is symmetry-adapted perturbation theory with multi-configurational wave function descriptions of monomers. So the idea is that imagine you want to compute interaction energy for 2 molecules. So first you have to use your external code that you like to run wave function calculations for the monomers. Out of that, you need to generate density matrices, again, only 1 and 2 electron density matrices for both monomers, and you plug these in to GAMCore. And the result from GAMCore is the interaction energy, but it's not just one number because the interaction energy is decomposed into the components. Each component has a physical meaning. So we have electrostatic plus exchange plus induction and plus dispersion components, which sum up to the total interaction energy. So as a result, you can interpret the molecular interaction in terms of the physics of or the mechanism of the interaction. or the mechanism that binds two molecules together. And now the special feature, the unique feature, I would say, of the code and the method which is in the code is that we can run these kind of calculations for molecules, for complexes which are not necessarily in the ground states, but they could be in electronically excited states, or they could be in open shell states, or molecules could be out of equilibrium geometries with elongated bonds, for example. So the recent developments for this part of the code is that we have added the generation of two electron integrals on the fly with Cholesky decomposition, which push the boundary of the capabilities of the code to larger systems, to medium-size complexes. And we have also implemented a new algorithm for calculation of the dispersion energy, which is the most costly part of this calculation. And this allowed us to reduce the computational scaling of the method from the n to the 6 to n to the 5, where n is the size of the system, right? So the scaling goes on with the 5th power. I'm saying only because comparing to other ab initio methods, it's not a lot. So the cost goes with the 5th power of the system size. And this is an example of the calculation that you can run. So imagine and this is actually what we have done recently. So we have investigated how the interaction changes when you excite the molecules in the bound complexes. So here we have anisole, this is the larger molecule, interacting with ammonia. So, and then the question was what happened with the binding, the interaction, how the interaction changes when you excite anisole. So we generate a localized exciton on the anisole molecule, and we investigate how the interaction has changed and which component has changed. So we could show that the interaction is increased, right? So the binding increased, the molecule is more strongly bounded. And this is due to the electrostatic and the dispersion and induction effects. So these increase and they put the monomers closer and they are bounded stronger. So this was the cutting edge calculation for GAMCore, where we ran CAS calculations for monomers, and the number of basis set functions is, as you could see, more than 1,000. So it's 1,200 basis set functions. Okay, so these were the examples of the calculations. GAMCore is an open source code, and you can download it freely. It's publicly available. There's also an installation guide and the user manual available. So you can download the code and explore the capabilities. And also you can find some examples in the manual to play with the code. Okay, thank you for your attention.
Thanks a lot, Kasia, for the presentation. I also remind you all that these presentations will be available from the TREX website event page, so you can access them from there. You will be able to do so very soon, so you can also find all those links that have been presented. So I don't see any questions, so I welcome Kosuke Nakano, former researcher at CISA, now staff scientist at the National Institute for Materials Science in Japan, who is going to give an overview of Turbo RBB.
Thank you very much, Sarah. Can you hear me?
Yes.
Okay, I'll start. So, okay, I'm talking about the Turbo RBB package today. So the Turbo RBB package is it's composed of 3 packages. The first one is Turbo RBB, which is a quantum Monte Carlo kernel. Okay, another one is Turbo Genius, which is Python wrappers and also for command line interfaces for Turbo RBB. And the other one is Turbo Workflows, which is workflow package. So to manage Turbo RBB jobs by Python. So all the 3 packages are available online, so they are open source. So you can download them from our GitHub website. Okay, so Turbo RBB features are, let's say, the first of all, Turbo RBB is tau RVV implements variation Monte Carlo, real space quantum Monte Carlo methods, variation Monte Carlo, and lattice regularized diffusion Monte Carlo. Okay, and this code implements very flexible ansatz such as anti-symmetrized general power and Pathian, by which we can go beyond the standard Slater determinant ansatz. Okay, the third feature is tab RVV allows us to compute atomic forces and also pressures thanks to the implementation of the algorithmic differentiation developed by Professor Sandro. And finally, okay, the tab RVV is very efficiently parallelized by MPI, OpenMP, hybrid, and also GPU. So as I mentioned, now you can control tab RVV job by Python script. So like this, I am showing an example like here. So yeah, now it has become let's say more user friendly. And if you are interested in the details of this Python packages, so you can have a look at our paper recently published in Journal of Chemical Physics, in which we reported not only the implementation but also the benchmark tests, okay, using turbo workflows. Okay, so now, as mentioned in the Professor Kasuda's presentation, one of the main achievements in this TREX project is this TREX IO format, by which we can convert wave function, right? So for instance, Turbo RVV has our own DFT code, but it does not implement, for instance, DFT plus U. So now we have implemented a converter, many converters from existing DFT codes such as PySCF and Crystal 23, Orca, and quantum package. So now you can generate trial wave functions using these DFT codes, and then you can convert a wave function from here to here, and then now you can initialize variation Monte Carlo or diffusion Monte Carlo wave functions of tau RVV. Yes, using this code. So this, okay, so now I'm showing 5 useful links. So here, so this is our website. You can see this our website about information about the Turbo RVV, and you can also download Turbo RVV from this GitHub, Turbo Genius from GitHub workflows, and we have also a collection of tutorials because we had several summer schools of Turbo RVV, yes, during this TREX project. So now I have 5 minutes, right? So okay, recently so this is another topic about recent progress using Turbo RVV is we have recently established a way to compute unbiased variation Monte Carlo forces by Turbo RVV. So if you're interested in the detail, you can refer to this archive paper. So a problem of variation Monte Carlo force calculation is sometimes it is biased. Biased means the computed atomic forces are not consistent with the derivatives of potential energy surface. This happens because sometimes we cannot optimize all variation parameters included in the ansatz, the wave function, because sometimes the number of variation parameters becomes let's say million or sometimes trillion. So it is a well-known problem in the quantum chemistry community, but it is not in quantum Monte Carlo community. So we have recently established. So first of all, I can show an example. So here I computed equation states of the cubic boron nitride. The left one was computed using quantum espresso. And the green block line is the numerical derivative of the potential and energy surface, the green solid line. And the red line represents the analytical derivative computed by directly computed by the gradient. This gradient was directly computed by quantum espresso. So in DFT, there's no bias because the Hellman-Feynman force is exact as far as the basis set is complete. So we can see the complete consistency right here, right? But in variation Monte Carlo, if we do not optimize all the variation parameters included in the ansatz, we see some difference, bias. So now in the paper I showed in the previous slide, we proposed to correct this the additional term at the variation Monte Carlo level, and then we showed that we can get unbiased variation Monte Carlo forces using our method. Okay, so the several perspectives for users. So now we are refactoring TurboRBB, and also we are now making documentations and tutorials better, more user-friendly for users. So anyway, so any suggestion is appreciated. So if you have some questions or let's say requests, please contact me. Thank you very much.
Thank you very much, Kazuka. We do have a question, actually. Shibu Meher is asking, can we use the wave function from Quantum Espresso in Turbo RBB?
Yes, unfortunately, no, at present, because TurboRBB employs a localized basis set, while Quantum Espresso uses the plane wave, right? So in principle, I think it's possible by implementing some converter from plane wave to localized basis set, but we don't have it right now.
Thanks, Kazuka. And of course, if you need any more clarifications, we will also share contact details via the TREX project for the for the owners of the codes. Okay, so thanks a lot, Kazuka. And now I welcome Abdallah Ammar, postdoctoral research at CNRS, to present QMCkl.
Hello everyone. Today I will present the code of Anthony Semama. Unfortunately he is not able to present it. So QMCkl is also another program to do a Monte Carlo in real space. And so it allows to do variation Monte Carlo and diffusion Monte Carlo variants with a CI Gestro ansatz, where the main advantage is the possibility of handling very large expansion in very efficient way. So the reason why QMCkl is very efficient, it's because of all the single core work is done with very optimized, with very highly optimized code, thanks to the collaboration of William Jalby from Versailles, and also because also single core subroutines are based on QMCkl, which is a high performance kernel for Monte Carlo. So, and another feature of QMCkl, it's the ability of handling fault tolerance. So if you are running a calculation on 100 nodes, and then there's one node where the calculation where you have a problem with the calculation, you will not lose all the data because of this fault tolerance implementation. So a lot of benchmarks was run using QMCkl, but here I would like to mention this one, which was run on the larger French supercomputer with more than 67,000 CPUs, and so the performance of QMCkl achieved like 30% of the theoretical peak performance, which is very high, which is considered as very high performance. So, and finally, just to give an application using QMCkl. So here I would like to mention that this code was used to generate the most exact variational ground state energy for the water using again CI Justro ansatz, where the CI part is based on Slater determinants expansion generated by quantum package. So Emmanuel Giner will talk about this code after. And the algorithm used was fixed node diffusion Monte Carlo. So the recent work done here with TREX using QMCkl was to optimize CI Justro wave function. So a CI Justro wave function. In a CI Justro ansatz, you have a CI part, which is a linear expansion of Slater determinants, and a Justro factor. So the goal in the TREX project was to optimize the parameters of this wave function to get accurate results. So when we talk about parameters, we talk about usually molecular orbitals, linear coefficients in the CI part, and also on the other hand, the parameters in the Justro. So usually in Monte Carlo, we optimize all these parameters stochastically in a variational Monte Carlo framework. But our goal here is related to the work presented by Ali before. So instead of doing all the optimization stochastically, what we do is we employ the transcorrelated approach in order to optimize the CI parameters in a deterministic way without statistical errors, and we optimize the parameters of the Justro in a statistical framework. So just a few words about the transcorrelated approach, which allows to optimize everything here in a deterministic way. So the transcorrelated Hamiltonian is a similarity transformation of the usual Hamiltonian with the Justro factor. So as mentioned by Ali, it's a three-body operator, and it's non-Hermitian. But as you will see in the next slide, even if it's non-Hermitian, it allows to optimize the wave function with no problem. So just one illustration of the use of QMCkl to optimize the wave function. So here we consider a wave function with just one determinant and one Justro. So the idea is to start with some initial choice of the Justro. Then we optimize the orbitals using the transcorrelated framework. So this part is done using quantum package. Then we estimate the variational Monte Carlo energy using QMCkl, and then we update the Justro and we iterate. So by doing that, so here an illustration for the water molecule in augmented VTZ basis, where we employ this algorithm to optimize 5 parameters. So as we see at the end, we are lowering the energy. So so we don't have any problem with the non-hermeticity of transcorrelated approach, and also we have a huge gain because it's much faster than an optimization based on stochastical algorithm. And if you have any question, you can ask me, and if you want to, you can find the code here on GitHub also if you want to install it. Thank you.
Thanks a lot, Abdallah. There is a question which I'm not sure is just for you or for the speakers that presented before. I read it aloud. So what is the basis of QMC in the sense are there any parameter computed by DFB that could be used in quantum Monte Carlo? Yeah.
So yeah, it's a general question, but so a brief answer. Basically, you can use some ansatz which come from DFT, but the main advantage of quantum Monte Carlo is that you can use anything. So if you can use anything, you would prefer to use something that you can improve systematically. So you would prefer to use something based on wave function theory. But I can let also if Ali or the other would like to answer, but yes.
Yeah, Ali had to leave. I don't know if he's any of the other speakers who wants to complement the response for our user or yeah.
Yes, I do.
Yeah, thanks, Kazuki.
Yeah, it depends on the implementation of QMC. It's my answer, let's say, because so some QMC code employs plane wave. So in that case, for instance, quantum espresso can be used for generating wave functions. And for instance, my code TabRBB, as I told you, we use a localized basis set, right? So in that case, so it is not very straightforward to use quantum espresso for generating trial wave functions. Instead, we can use the PySF, for instance, because the PySF employs a localized basis set, both for open and periodic systems. So basically, the limitation is not a theoretical one, but practical one.
Thanks. Thank you both. And thanks, Abdallah, for the overview. Now we move on. We have a couple of codes left. So now I welcome Ravindra Shinde, research scientist at the University of Twente, who I thank even more since I know he's commuting, so he's joining phone. So I'm happy to share your slides. Give me a second.
Thank you, Sarah.
Okay, you should be able to see it. So when we're ready.
Yeah, thank you. Hi, good afternoon. I'm Ravindra from University of Twente, Netherlands. And pardon me for the background noise. I'm on a train. So today I'll be presenting CHAMP, Cornell Holland Ab initio materials package code. This is the Netherlands version of the original CHAMP, which was started in Cornell. Yeah, and this is a suite of programs for accurate electronic structure calculations using quantum Monte Carlo. And it can handle molecular as well as periodic systems. We recently added this functionality for periodic systems. The main features of this code are the efficient optimization schemes for ground and excited states in VMC. It's very efficient. It's highly optimized code. Recently, we also implemented state-specific energy minimization. So you can select states and then minimize energies with respect to the parameters of the wave function. We can do also analytical intraatomic forces with VMC. and this code is specialized in fast evaluation of multi-determinants and their derivatives. We can also use multi-scale hybrid QMC calculations with CHAMP. So CHAMP is mainly written in modern Fortran. It has been improved a lot during this TREX period. So I will be showcasing a few examples here on the next page. So the first one is geometry optimization for a varied number of determinants for a small to large molecule. And here you can see that the cost of calculating energy as well as forces is just 3 times the cost of calculating energy only. On the next page, we can do a wave function optimization for a large number of determinants. So it's only practically limited by the resources. We can go a very high number of determinants with this code, and the evaluation of energy as well as derivatives is quite optimized. On the next page, we can see that we can use both the geometry as well as wave function optimization together simultaneously, and it doesn't depend on the initial wave function we use. You can use any initial set of orbitals to start with. And this is an example of an organic molecule which we optimize. With the TREX, we have coupled this code, CHAMP code, with other quantum chemistry codes via TREX-IO. And this has helped us a lot to standardize our input system. The input file has become very smaller and much cleaner because of the TREX-IO. And I will show you later on this page, later in this slide, that we have achieved great MPI performance also with the TREX-IO. So this is another implementation from the TREX suite of codes. It's QMCkl, Quantum Monte Carlo kernel library. We have also implemented that inside the CHAMP code natively. So you can just call the Quantum Monte Carlo kernels within the CHAMP code. And this has improved the performance a lot within the CHAMP. We have successfully ported this on top 10 supercomputers in the world, such as Lumi and Fugaku. On the next page, this is a case study of C60 molecule, and we were testing the performance of parallelization. On the left-hand side, we can see the weak scaling, which is nearly perfect until 5,000 CPU cores. And on the right-hand side, we can see the strong scaling up to 25,000 cores, which is very nice, and which is rarely seen with the other codes. So on the next page, we can get the code. It's freely available GPL3 license from the GitHub. You can find the user manual also. And if you have any questions, you can just drop an email to me or the other code developers. Thank you.
Thanks a lot, Ravindra. There is a question. I think it's for you, yes. What do you mean by state-specific minimization? Is it the wave function optimization for a particular electronic arrangement?
Yes, so you can optimize a specific state, let's say, for example, first excited state or the second excited state. And the parameters of that wave function. You can the computational chemistry group University of Twente. We recently published this in JCTC.
Yeah, you're breaking a little bit, Ravindra. we'll make sure maybe Shibi, if you want to write us, we can put in contact also with Ravindra. He's also asking what is the maximum number of electrons CHAMP can handle. So I'm not sure, Ravindra, if you're still
Yes.
there. Yes.
So there is no limit as such. We studied the last plot which I showed is for fullerene C60. So practically there is no limit. It depends on how big is your computational resources. So generally, if you go on higher end supercomputers, it will be limited only by the RAM, which is there per core. So you can handle
Thanks.
very big
Yeah.
systems. Yeah.
Thanks, Ravindra. I think it was clear enough. Okay. So now we're moving toward the ends of our series of presentations, and I welcome Emmanuel Ginet, CNRS, for introducing us to Quantum Package.
Okay, thank you very much. So, okay, I will I will share my screen. Okay, you see my screen?
Yes,
Okay.
yeah, perfect. Yeah.
Great, thank you. So, yeah, I will briefly sketch out what are the main features of the quantum package and how we design this with essentially with Anthony Simama. So the idea was to build an electronic structure code which was developer friendly, and yeah, I think it's not perfect, but it has some good features. So let me give you a little bit of context, maybe. So from the developer perspective, in quantum chemistry, you have the kind of code dilemma, which comes from the paradox of quantum chemistry codes, because you need an HPC software because you have a large amount of data to handle. You need to do a lot of flops, but on the other side, you have very hard problems to solve, which imply very complicated algorithms, and therefore you need a flexible coding environment. So there's a kind of paradox because, of course, HPC and flexible codes, they do not go along very well, essentially. So the typical developer's need can be sketched out like this. So you have a new idea, which you think is very fancy, that can tackle an unsolved problem. And so therefore, what you think, what you want to do can be eventually boiled down to the fact that you have a new set of mathematical equations to solve, which is like, new theory. And for that, you need to feed this set of mathematical equations with some physical quantities that are essentially the data that you are going to feed in your model. So what you need eventually is some easy access and combination to key quantities. So first, you need, at the end of the day, matrix elements. So the matrix elements will be eventually these physical quantities that you are going to feed in your mathematical model. And also you will use linear algebra routines, or not even linear, but let's say complex mathematical routines to solve essentially these equations. And also you want to do this by handling, I would say, complicated data storage in the sense that typically you have a lot of these physical quantities, so they cannot be stored naively. So essentially you have to work on this. So you want this to be efficient enough to test your idea on a real system. So you have the beta version, which is easy, which is like a beta implementation of the code that works for small models. So essentially to verify that what you're proposing is not crap. And then, of course, you want to make it scale on larger system, and that's really the hard problem. Okay, and also, what you would like is to essentially enter in the community, which means that all the blood and pain that you suffered for developing your code, you want to maximize its impact in the community. So therefore, you want to diffuse the code as much as you can. And also to have bug reports, because of course, you cannot find all the bugs by yourself. You also let the users do it for you essentially, and that's the so-called mutual benefits of the collaboration between the developers and the users. So that's typically the developers' need, I would say. And so when we started this project almost 15 years ago, the typical situation was that you had available codes which were kind of old but efficient. So they used rather ancient but efficient languages like C, like Fortran 77 or 90. They were not necessarily open source, and from the outsider's point of view, it was a nightmare to get your hands on what you need, like some kind of integrals or matrix elements or whatever. So that's why we designed the quantum package essentially as a response to this situation. And long story short, the idea was to have highly optimized fundamental building blocks and a modular structure for eventually you just have to pick what you aim for, and you don't have to understand all the 100,000 lines of code because that's a pain. And we also insisted on designing a plugin system that I'm going to briefly describe in order for you to easily create your own code. So we have some documentation material that essentially is here, at our GitHub page website, okay, where you have here, so read the doc documentation, which is, of course, as all the documentation is not perfect, but it exists, and I think that you can kind of do some stuff with it. We have a set of tutorials, which are also available on YouTube and that you can still find there. And we also have a try in your browser interface, which is quite nice because you can essentially try the quantum package without installing it. You can, like, in a few minutes try this, and essentially you can do the tutorials in your browser. That's the idea. So let me enter a little bit more in the details, so to say, of how the quantum package was solved. So the idea is to have a kind of modular language, which is a modified Fortran 90 language, so-called IRPF90, that Anthony Semama designed. And the idea is that it handles all the complex dependency of variables. So for instance, if you are interested in the two-electron integrals on the MO basis, you know that it depends on the two-electron integrals on the AO basis, but also on the MO coefficients, with themselves can depend on of course, on the electronic coordinates, on the exponents of the Gaussians, and so on and so on. So you have a tree of complexity of dependency, which essentially scales exponentially with your code, and that's really complicated to remember, okay? And so that's why Anthony designed this IRPF90, which is open source and available for any of your code, and that essentially handles all the complex dependencies of all the variables by essentially reading your code by a Python script, and eventually at the end of the day you just use the quantities that you want. So you don't need to know essentially how they are built. You only need to know what they are. So that's a huge burden relief, so to say. So that's the modular language. And based on this, we started a modular structure, because we have essentially core quantum chemistry objects, which are essentially integrals with the efficient data storage which is involved, Slater determinants manipulation, because when you do quantum chemistry, very soon you will have to manipulate Slater determinants. We have also, of course, Hartree-Fock routines, DFT quantities, and the highly efficient selected CI code. That's essentially the core of the quantum package, with a parallel efficiency close to 100%, up to 6,000 CPUs, and close to essentially 80% with 20,000. So still, it's scale up. And we also have a highly optimized couple cluster code, but essentially all that is the core of the quantum package. And on top of that, you have the plugin system, which is basically the developer's playground, okay? Where you have, it's a set of external codes and routines that are easy to install and to connect with these core objects. So essentially all the stuff that you have here, you can of course use them in the plugins, and it's very easy to essentially connect and to exploit all the all the stuff that are here, essentially. So we design a CAS-SCF, weird flavors of DFT, transcorrelation, as Abdallah was mentioning. And the idea is that based on this, you can easily create yours. And I want to write to make a video of a simple tutorial in order to guide you, but I still did not find the time to do it. So maybe a few examples of application of the code still from the developer's perspective. I will not give you any numbers or this kind of stuff, but just to give you an idea of the quantum package community. So it is used and developed mainly in Europe, so in France and also in Poland, with thanks to Kasha. Also in North America with our collaborators in the US and in the Canada. Our main product, so to say, is ground state and excited state calculation with the selected CI code, the very optimized code that I mentioned. So it's really like state-of-the-art calculation to obtain near full CI results. Okay. So as an application, for instance, you had the benchmark of Pierre-François Loss and his collaborators to compute excited states of weird molecules, and the typical size that you can reach is benzene. To give you an idea. So that's one main, let's say, application. And then you have a lot of, let's say, a lot of theories or stuff that have flourished, essentially, thanks to the versatility of the quantum package. So for instance, multi-reference range-separated DFT that I did with Julien Toulouse. I also designed some positron binding calculations. We have also transcorrelation. That's what Abdallah essentially mentioned. Abdallah also did complex Gaussian basis. We have also an application to core excitation / ionization with Anthony Ferté. So Kasha and her collaborators, they also use the quantum package to feed in their multi-reference adiabatic connection code. We also have selected CI for quantum Monte Carlo in the US, some extension to solid state physics. Also, Piotr Piekuk use the QP to do high-level couplet cluster. We also have some. And we have other stuff that I do not mention because I don't know them essentially. But yeah, so just to tell you that the quantum package has, the idea is to have a kind of versatile code, and it's relatively easy to do what you want. And so with that, I would like to conclude and just to tell you that if you want to know more, just visit our website. We have our tutorials here, so you might see some videos with me speaking like a YouTuber and explaining to you how to do your first step with the quantum package. You have the documentation and the try in the browser, and of course the source code with GitHub. So yeah, that was essentially the idea of sketching up the quantum package. Thank you for your attention, and I'll be happy to answer any questions. Thank you.
Thanks a lot, Emmanuel. There is a question still by Shiva, which can be, I mean, the $1,000,000 question. So
okay.
Yeah, I know. When I say I never developed any scientific software, but I have keen interest in scientific software development. I've written small codes to perform pre and post processing for quantum chemistry code. What do I suggest? What do you suggest that I should do to get started?
Oh, that's a big question. Well, it depends. It depends essentially what you want as a. So I'm not sure to exactly know. I mean, to fully understand the question. What do you suggest that I should do to get started? So if you want to start some scientific software, like if you want to start playing with quantum chemistry codes, well, I would suggest maybe you to try to implement some Hartree-Fock code, and for that you essentially need 1 and 2 electron integrals. So that's something that you can try to, to begin with, I would say. And so just get a code like the quantum package or any other code, of course, and get the integrals and yeah, and then play with it. That would be my reply.
Any other suggestions from any audio speakers before? I mean, I would say it's a pity you only discovered us now, because we've been gone through a series of training activities over the last 3 years. So, I mean, we can go back in time, but one of the things you can for sure do now is browse a little bit what the TREX Center of Excellence has done since all the works and codes developed there. We continue in a way or another through the partner institutes that have contributed to. So getting in touch with them is one of the ways to continue growing your interest. Are there any other questions? Okay, if no, maybe I can wrap up by inviting you to browse a little bit the materials that you can see and find on our website as our speakers presented. The entry points for the different repositories can be accessed from the public website. So there is a menu dedicated to our TREX codes, and from there you can find initial information on the contributors and the materials available and supporting the code's evolution. We also invite you to have a look at the events that were organized, because there you can find additional information both for training purposes. So in many of the cases where we organized workshops in summer school, we made available presentations through Zenodo or GitHub, so feel free to browse them. And I also invite you to stay tuned, because last couple of weeks ago, TREX organized its symposium in Luxembourg, and its program is of course available, and we are publishing the slides presented. So it was a unique and its type event for quantum Monte Carlo chemistry community, who brought together an impressive number of experts from all around the world to debate on recent QMC developments. So for sure, stay tuned and you'll learn more. The TREX Center of Excellence was funded by the Horizon Europe program of the European Commission, and is meant to conclude in March this year. But the legacy and the extremely collaborative work that the project has developed and the co-designed approach that has installed in the community will remain. So all the contacts will be there, available even afterwards, and we will be happy to facilitate any contact with the communities behind the TREX codes. So if there are no more questions, I'm happy to thank our speakers for presenting today, and I thank you, all of you, for attending. The recording of the webinar will also be published online soon, and feel free to get in touch with us, and stay tuned for a hopefully next phase of the TREX Center of Excellence. Thank you all.
Thank you.
Bye.
Thank you. Goodbye.
Bye. Thank you.